So, hello, everyone, to this session of Paper Club. Uh, Today we'll be reading this interesting paper called Some Studies in Machine Learning Using the Game of Checkers uh, by A.L. Samuel, Arthur Samuel, I think most known as it's known. From July 1959, so pretty old paper, published on the IBM Journal of Research and Development. So just some motivation before starting the paper itself. This is one of the foundational papers for what we today call AI and machine learning. So let's do the mental exercise of pretending that we don't know nothing about like AI and machine learning. Because in this paper, we will investigate some approaches of implementing like self-learning algorithm on a computer. So I can remember like previously to studying like machine learning on college. Like I couldn't figure out how you would make a computer learn. So I thought like maybe we will do like this code that creates a bunch of ifs and else's dynamically, and then this is like machine learning. So I don't know. Let's go back to that mental state of not knowing things, and let's try to understand, or at least get some notion of these first approaches, and then we can like reflect of how this paper became very important for like areas of machine learning and AI today. So cool. Let's have the pointer. So as a summary, we will see mainly two approaches in using the game of checkers. So in Portuguese, like if you don't know checkers, is dama, jogo de damas. And it's not chess, because chess is more complicated. I think that's annotated also on the presentation. And the focus of the paper is to investigate the learning process itself. So yeah, the paper will also demonstrate that a computer can surpass the programmer's gameplay skill. I think this was a surprising thing at the time. Also, another thing that was important that we'll see that it learned with minimal input, and like I will also added like these notes about like performance. So this they say that the learning occurs rapidly, like around 10 hours of playtime. For us nowadays, like 10 times is huge. Like wouldn't so we wouldn't say rapidly, but I think that's interesting to note. And also, like the paper will suggest that learning can automate complex problem solving beyond board games. So maybe, let's see. Cool, so this is a summary. Introduction. The paper says like what they will call machine learning is the ability of computers to improve their performance on tasks through experience without being explicitly programmed for every detail. So if the programmer needs to come up with an algorithm that solves all problems, then it isn't like machine learning. We need to simplify the algorithm, and it should learn by itself how to deal with complex scenarios. So as I said, like this will focus on programming the computer to learn through self-play, and not only self-play, we will see as well. And why checkers? As I mentioned, like this is a well-defined problem with a space like with clear rules and objectives. So it's easy kind of to make like a evaluator that checks if the computer is playing according to the rules. And also this is a controlled environment, like controlled environment. So yeah, the motivation on the paper, like traditional programming requires explicitly instructions, and also machine learning should reduce human effort. And yeah, understanding this would help us to generalize to broader AI applications. So as we can see, like, pretending that we don't know AI. I think this is a pretty interesting motivation and setup. So yeah, about the author, like, I don't think many people remember Arthur Samuel. Like, this guy was important, was a pioneer, but I don't think many people reference him about being a pioneer. Like, I think he coined, like, machine learning in this paper that I'm presenting. Yeah, he developed, like, this checkers program at IBM, and was on the first AI applications. And he worked at Bell Labs. If you don't know Bell Labs, maybe you should know that they kind of invented the transistor. So pretty important. Also, like, I worked on the ELIAC project. Was I think one of the first supercomputers ever to be, like, implemented, and also IBM and on AI research and Stanford. So this guy was pretty important on the field. And yeah, I think we can go past. But one final notice is that he was like a I3E computer pioneer. He received the Computer Pioneer Award. Cool. So let's see how the paper first approaches this learning schema. So, like, quoting from the paper itself, like, it says that we will distinguish sharply between two general approaches. One approach, which might be called neural net, is like learned behavior into randomly connected switching net, and as a result of reward and punishment routine. So remember that this paper is before backpropagation and loss functions and etc. So we can, and, like, reinforcement learning wasn't a term as well. So pretty interesting that they were already, like, saying that this was like a possibility. I forgot, like, which paper, like, introduced the idea of mathematical neurons. I don't remember if it was before or after this, but yeah, interesting. And the paper also, like, defines the second approach, which is more efficient, which is produce the equivalent of a highly organized network. So the previous was a random network, and this second is designed to learn a specific task. So already we are talking about specializing a model to solve a specific task and not be a general model by itself. And also, quoting the paper, like, the first method should generalize, as I was mentioning, like, nice, Gabriel, thank you. So 1 year before, perceptrons were already introduced. And the second requires reprogramming for each new application, but is capable of realization at the present time. So they focused on the second because they thought that the first wasn't possible with the computer processing power that they had at the time. So yeah, let's see how they did the second. Lastly, I think also quoting the paper, like, they chose checkers due to simple rules compared to chess, allowing greater focus on learning techniques. And also we have a clear, well-defined set of rules, success criterion, and familiar context that enables evaluation against human players. So yeah. And also, final remark, like, I think he was working at IBM at the time, so some of the comments on the paper kind of serves as to highlight how IBM 704 is a good processor or computer. I don't know. Like, there is a detail. We won't go into this detail on the paper, but he mentioned, like, the memory word size is optimal for storing the game rewards, etc. So cool. Yeah. So yeah, let's see how we can build a basic checker playing program. So what we will do is simulate human decision making. The paper says it, not me. So we will look ahead a few moves and evaluate board's position and choose the best move based on a scoring system. So kind of a human, as they say, like, you see, like, if I do this, then the opponent does that. That's bad for me. So similar, but simplified. So yeah, we will compute all possible next moves recursively, generating new board positions and scoring them based on a polynomial function. So yeah, this is important, like the polynomial function. We as humans don't have like a explicit polynomial function. And like the scoring method, the polynomial function prioritizes key aspects. The most critical is whether a player can still move, which is checked separately. The program then evaluates piece advantage, favoring reductions in opponent's pieces. So this is like one of the important terms of the polynomial function for scoring. Also, like I think it's important to notice this comment, like if the sign of this parameter were reversed, the program would instead optimize for giveaway checkers. So this is like optimization polynomial function, classical optimization problem, and they are already discussing like the meaning or semantic of each coefficient of this polynomial. We will see a little bit better in the next slides. So yeah, very basic checker playing program. So another important comment is like the selection of scoring parameters and their coefficients can be determined either manually by the experimenter or automatically by the program. And we will see how they can adjust automatically. But the first approach would be to program manually, like paying attention to the signs and etc. And it's also written like initially the experimenter defines these parameters with later sections exploring methods for the programming to adjust them dynamically, as we will see. One thing that is important is that during this recursive evaluation, and now we'll show this on an image, I think on the next slide or some slide ahead, will be here at some point, is that we cannot like just select the highest scoring move, because this is impractical. So this is an important notice that the paper says, because this assumes the opponent cooperation. We need instead to employ a minimax algorithm where we assume that the opponent will minimize its score while maximizing its own. So the opponent must play the best possible position for day, and we will play the best possible move or position for us. So we need to do this switching between when choosing our best move, because we cannot like just maximize our gain, because we cannot assume opponent cooperation. And once the best move is chosen, it is executed, displaying the console and logged. The opponent moves then enter manually, etc., 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 and then we cycle through this until we arrive at a final end of game position. So cool. Let's check very briefly what that polynomial might be. So very simple definition. We just define like a bunch of terms, which are the F's, which are features. And then we define a bunch of W's, which are the weights of each feature or coefficient. We can think that as a linear evaluation function. And we are defining like what is important, what features are important, and how much each feature are important to the scoring function. If we want to maximize, like we need to give positive values to our advantage. And if we want to minimize, then we must give negative values. Some of those features that were defined by the paper, like piece advantage, more pieces than the opponent is important. King advantage, kings are more valuable than regular pieces. And they define this 3-to-2 weight ratio. Positional advantage, like central pieces, is favored. Mobility advantage, the number of legal moves is also beneficial. And we also like check the minimax score adjustment, as I was mentioning. Cool. Let's see how to choose this best possible, how to play the game automatically, like without explicitly programming the plays. So this is called rote learning, which is how to choose the sequence of decisions to win the game. So this is a very simplified. Each node here has like a score of the what would be like our score after if we follow this route of play. So remember, we cannot assume opponent cooperation, so we must do the minimax thing. So it's highlighted here the best play for us, and we can see that we have like this position with what is plus 100, but we do not follow this route because the opponent, when we do this play, it won't like give us more advantage. The opponent will try to play against us, so it's decreased to plus 20. And then afterwards, when it's our time again, like we play the plus 20 move. So this is why we cannot just maximize these decisions. And we introduce here this concept of ply number, which defines like how deep on this recursive possibility tree we are before evaluating the game. Because notice, on these nodes, we are not evaluating that polynomial. We are like just generating the possibilities. And then when we reach this level, then we evaluate the possibilities to choose this route. So this is how the game is played by this algorithm. And like we could simplify things and just say like, let's define 3 as the number, but they actually implemented some dynamic ply limitations, like or dynamic ply adjustment. So we won't fix it at 3, but depending on the situation, we can like increase the number of evaluations from branch to branch. So this tree won't be like exactly complete each time. Like if we arrive here and check some condition, then we can continue generating recursive plays to see if this branch will actually be better or not. So some of those decisions of extending the search or stopping, it's kind of like 3 is the basic, but if we, the next move is a jump, or the last move was a jump, or an exchange offer is possible, then it continued generating possibility in place. And then like we have this detail here of like how much we can evaluate that tree. I don't think we need to enter in those details, but like we can check like at the depth 20, it will stop due to memory limits. So pretty interesting that for us nowadays, this should be very shallow regarding our memory capabilities, but they couldn't like generate more simulations at the time. And also, if we think about like chess playing programs or like the AlphaGo program, like it won't stop at depth 20, and we'll do that many times during its play, and not even like programming those explicitly like this is programmed here. Cool. So just like this is the first possibility of how we play the game. Let's see just here. Yeah, they explain like why we should like adjust this ply depth due to board conditions, but I think pretty much it covers what I was saying. Like we can like evaluate only on stable positions with those rules like of jumps and exchanges. So we avoid those dead positions. We also increase the focus on moves that offer better chances to gain or lose advantage. Like we won't stop before gaining a piece advantage. It's more interesting to evaluate afterwards that. And yeah, I also like, it's another important remark, jumps limit branching because it reduces the game space because we have fewer possible combinations and plays possible because we have fewer pieces. And yeah, I think important comment. Finally, they also implemented this practicality of only allowing the computer to think 30 seconds per move. So to choose the route or the best play at one position, like it would think for at most 30 seconds. That's why they had to implement like table lookup procedures, fast sorting, searching, etc., etc. And as I was mentioned, like they promote the IBM 704 here, because like we made full use of the resources of this processor, so we could play at 30 seconds with this complex tree search evaluation. Yeah, nice. So yeah, this is a very simple way of playing. Like you have that scoring polynomial, then you do this simulation recursively to choose which position you play at that time. But they implemented other modes of play. And here we can see how things ended up where we are nowadays, folks. So the first proposition they do is self-play. Like the program can play against itself, controlling both sides of the game. So that would be known, I think, as what we call today like reinforcement learning. Like we have OpenAI, I think, started with programming reinforcement algorithm to play StarCraft 2, or they had this project some time ago. Was pretty interesting because they were able to beat pros, I think, on StarCraft 2. Then Dota 2, as Tavares mentioned. And they did that with pure reinforcement learning, I think. I don't recall specifically how they implemented, but I think they gave the commands much more complex than what we are doing here. But I think they gave the possible inputs and then some reward function. But this is the very first, I think, iteration of that idea. And they also implemented playing against recorded book games. So this is also pretty interesting because like suppose they have like pro games played recorded, they could try to simulate that game, predefined expert games, and like they could evaluate if the program proposed move would how it would compare to the recorded book move, and then it can calculate a coefficient of correlation between those two, and to see if this algorithm can guess the best possible play. So this is pretty interesting. I think we'll give some details in a bit of why this is important, like regarding that polynomial that we were mentioning some slides ago. Cool. So those two modes of play. As I think it's important also to notice that since the paper wanted to focus on learning techniques, it didn't explicitly provide like human strategies or standard openings. So no special weight is given to optimal moves, even on those book games. And yeah, they just mentioned like you can start the game at any custom position to test like how the algorithm behaves on end games and puzzles, and we will see like how the various implementations or studies here differ on those situations for the game of checkers. Yeah, let's see. I think we can skip this. Yeah. No, I think this is important. Like we will see an optimization of our rote learning, because instead of scoring all encountered board positions against the computer scores, while this is not like an advanced method, we can still improve the performance by reducing redundant calculations, and this is important for the time. And this allows deeper look ahead over time. So if we say board positions at ply 1 instead of like going deeper, then we can reference them at higher ply levels, so we don't have to recalculate them. And the program can effectively extend the look-ahead depth. So yes, the example is if the program initially looks ahead 3 moves, which was the standard ply 3, and saves those board positions, we can later use them at ply 3, effectively treating them as ply 6 evaluations. So this process continues, gradually increasing the effective depth of analysis in future games. And when combining with rote learning, this approach enables a more powerful learning system, allowing the program to make more informed decisions based on previously encountered positions. So think about that original tree that we had, like we can arrive at the same board positions afterwards. So we don't need to store those two branches separately. We can just compute that board position score for us, and then we can reference that board position. We don't have like to have two different spaces in memory to that same computation because it's the same board. So we can, yeah, we can just, I think, yeah, this will be important when we talk about memory, but we can just encode the board configuration and then save this board with its score, and then we can just check our lookup table for scoring. So yeah, before using this star-based learning approach, we need a sense of direction to guide it towards the win. So without this, we could recognize winning position, but waste moves instead of advancing efficiently. So they will program like this sense of direction. So for example, in a two kings versus one winning setup, the program might see many possible moves leading to victory, but fail to prioritize the quickest path. To fix this, we track the ply value for each board position, and then we consider it when making decisions. So if ahead, we prioritize five faster wins by choosing lower ply moves. If behind, it delays the opponent by selecting higher ply moves. So remember when we chose the route, if we are winning, then we try to choose the path also that finishes the game with the shallower path. If we are behind, we try to delay, so the opponent may make a mistake and then we can recover somehow. This is achieved by slightly decreasing the score magnitude each time it's backed up to ply levels, ensuring that when faced with similar scores, the program picks the best strategic one. So yeah, this is just like biasing the choice, not only on score, but also with the ply value of that score. And here, it's also interesting that since we had memory constraints, we had to catalog and delete strategies for our memory, because we cannot like store every possibility on memory. So we have to standardize, classify, and selective forget to optimize both storage and retrieval. And I think they will, yeah, we will talk about the pruning and forgetting in just a minute. So yeah, just summarizing, we need to standardize and catalog board positions. Just giving more details, I just like gave the idea, and this is how they did. Like, to reduce redundancy, we need to store only board positions where it's white to move. So if it's black turn, they just invert the pieces and store it as if it was white to move. And also in game positions, like having the corners thing that I just mentioned, like two kings versus one in a corner, they reflect them symmetrically to avoid duplication of storage. And so they arrived at this compact board representation to allow them to store as much scoring and board positions on memory. And then they group records based on the number of pieces, piece advantage, presence of kings, more advantage, move advantage, sorry, and first moments of piece positions. So notice that they kind of encode the board based on what's important for that polynomial. So if none of these things change, maybe it will have the same score, so we don't need to encode other stuff to evaluate the board. So with this, we can catalog our board configurations into memory with a scoring, with a score for them. Yeah, I think we can go to step 2. Yeah, we can even like go to step 3, I think. But just like noticing how they had to do this because of the limitations of computation, like they had to implement like the LRU, less recent. I forgot what U was. Use, maybe. This is a type of cache based on the usage of each entry. So they remove from cache when they use the entry is not used. But this is kind of a hierarchy, memory hierarchy implementation. And I think what's important is the forgetting and expunging of these irrelevant positions. So they implement this frequency-based forgetting. So they argue that this is similar to how we do with our memory. So when we use things, they get like promoted in our brain, and otherwise we forget them. And they have like the age value of each board position, and they have this each time that they use that board position to computing some decision or rote learning. If they it's not referenced, they add by one, and after like some threshold, they delete that entry so they can compute or other board configuration and just keep useful board configuration. And they can also like do this ply-based, which is limit to low ply, remove low ply board positions first, because we can store like the deeply analyzed positions that will arrive at better advantage to us. Like the evaluating like just one move is not good, because we are not evaluating like the delayed reward of that move. So that's why they also implemented this culling based on the depth of that board position. And they said that this is like refreshing and forgetting is inspired by human memory and proved to be highly effective. So pretty interesting as well. It's like kind of reinforcement learning or reinforcement based memory, which is also used, we will see, to self-play later. Cool. So they also had, like, going back to that learning polynomial, they also had to test the learning system. And what they did is like, they, as I mentioned, like they could check like the plays against book moves and the correlation coefficients. And like the best performing polynomial had a correlation of 0.6 compared to 0.2 for the worst. And the final selected polynomial was based on those correlation coefficients. And it had like 4 key terms compared to 16 in later experiments, which was just piece advantage, denial of occupancy, mobility, and hybrid term combining. So yeah, this is kind of like just selecting a first model, and then later they can like add other features. But they did this selection based on the correlation with examples of good plays. So they had these recorded moves, book moves. So yeah. And they tested with self-play, human opponents, and book games. Important conclusions was that like it learned a strong opening game and recognized winning and losing endgame positions many moves in advance. However, mid-game performance was showed little improvement, indicating a limitation in rote learning. So the program achieved better than average novice level, but did not reach expert play. So pretty interesting that it learned like a strong opening move, because I think it highlights that importance of simulating like deeper positions, and like avoiding to choose like do the greedy optimization of some plays, and also showcases the importance of the learning polynomial. Yeah, some regards about like the problems with computer limitations, but yeah, won't spend much time here. But one thing that I think was interesting is that like at the current rate of data collection, achieving this would require excessive machine time. So I think that the problems are the same. We just changed like the order of magnitude of them. Like, and we still have problems with data collection requiring excessive machine time. Cool. So as we just saw, like this was the first iteration, like doing that rote learning to choose the best move. So kind of simulating and then choosing the path with the best reward at the end of it. So we can talk about like trying to generalize the learning based on past experience, saving useful abstractions. So I think we will now focus on the polynomial itself. So, but doing that automatically. So we should include multiple levels of abstraction. We can select each selected 16 evaluation terms from an available set of 38, so kind of feature selection here to construct the scoring polynomial. And the disadvantage term, which defines the task, is computed separately and remains fixed because they notice that this is important. And notice how this is related to checkers. Like going back to the first slide, we do not have like a completely abstract and general neural net. So how they allow the polynomial to evolve? They implement this alpha beta self-play for learning. And I don't know if AlphaGo and etc. Alpha X names that came later that also play games is inspired by this, but they do the self-play with alpha beta naming. So the program runs two versions, alpha and beta. Alpha continuously learns its evaluation polynomial, while beta uses a fixed evaluation polynomial. This is pretty interesting. So the alpha can play against human opponents as well, and alpha and beta compete. And at the end of each game, neutral evaluator compares alpha performance to beta. If alpha wins, the evaluator function, its evaluation function replaces beta. If beta wins, alpha receives a black mark. After 3 black marks, alpha polynomial is drastically modified to avoid getting stuck in local optima. So we do not have, like, as I mentioned, like neural nets, back propagation, learning rate, complex algorithms to change that. But we can see like the beginning of those ideas here, right? We check 2 possibilities. After some time, if things don't improve, like we try to always stuck this local optima, which are things that we discuss nowadays as well. And they also allow like the manual intervention for this polynomial. And how is the polynomial modification procedure? It's based on the performance. The solution is that, let me see what I want to say here. The look-ahead search reduces reliance on perfect evaluation because we can check if we will lose the game in some moves, because future board states matter more, like that delay reward of winning. And the goal is to align the current board with valuation with expected future evaluation. So it's just trying to check, like, if with this current board, if we play perfectly, we have an advantage at the future. And the closer the current evaluation mimics that final board position, the better the play. So if we can see that we are winning in a few moves right now, it's better for us, right? We don't need to arrive there by lucky. We can just like play well. Cool. So evaluating and adjusting that polynomial. So we track board evaluations errors. We'll call that delta. So alpha, which is the one playing that can change its polynomial, record each board position, and it's backed up evaluation. So before changing that polynomial. So the look ahead search for the final score effectively. So the difference between those two scores measures the error. So the initial evaluation, if it undervalue the position, then they increase the weight of positive contributing terms. If the initial evaluation overestimated the position, then it increased the weight of negative contributing terms. So yeah, no back propagation, but a way of trying to kind of reduce this delta, which we can call kind of a loss function for the perfect scoring, and or at least the true versus the Y prediction of our algorithm. And then we adjust, like we track the correlation between individual term contributions and the sign of delta. And after each move, correlation coefficients are updated based on how often each term was used and contributed meaningfully. So they can check like each feature, how it is correlated with that delta. And the most correlated term is assigned the highest coefficient. So like not back propagation, but like kind of saying that the highest derivatives should be updated more, the weight or the feature contributing more with the error or the loss function should be have a higher adjustment. And they do this like they constrain to powers of 2 for simplicity, and this like helps them to compute things. If the term's correlation becomes negative, the sign is flipped because that term contributes against like the score, the true score. They talk about some problems with instabilities, evaluation, when since we have like past remember moves and anticipated future moves, like the polynomial evolves with time, meaning that past boards might have been made with a different polynomial than the current one because it evolved. So after making a move and updated, we can recompute the score for the board position rather than using the original move determining score. Because we are computing score for future positions, we can recompute them to make sure that we are not like drastically comparing different things, since we are computing delta based on that. So this prevents oscillations, and they talk this is similar to feedback loops in electrical circuits. Not pretty useful to us here. And they talk about like to avoid excessive adjustments for small changes of that delta. We need to have a minimum delta threshold. So we avoid like changing the coefficients too much if we don't have like big error. We need at least some error to do that. Yeah, here they talk about newly introduced terms can have a problem. I won't talk about that. And here we have like the comment about like how we can decrease the influence of past and recent learning. So they come up with this kind of way of decreasing the importance of the past, to balance the past and newer experiences, like to ensure smooth updates instead of like noisy oscillations or large swings in correlation coefficients, as they talk here. Cool. Let's see. Yeah, not pretty interesting here. You guys can enter in the video later. So they also, I'll try to end up so we can have like space for questions. I think the main idea of the polynomial update is already explained. Let's see. They talk about like how we have like 38 features, different terms, with only 16 being active and 22 reserved. They also like removed the last correlated. Sorry, they track and they replace with some rule, and after some number of moves, they can like do the replacement, and they reevaluate like after 166 moves, etc., etc. Cool. So they arrived at this conclusion, which is generating terms autonomously is challenging, because like they had this manually generated list, hoping to cover important parameters, even if redundantly. Some terms are related to checker expert knowledge, while others are discovered by the program itself. For example, the second movement of piece position. No, I think I froze. I think I'm back. Yeah, the terms are related to relative standings, both sides, and expressed as difference between rating of sides, symmetry is maintained, etc., etc. But here is important to notice how it's difficult to generate the terms autonomously, like the difficulty with feature engineering. They were already experimented at the time, and they needed like expert knowledge to come up with those terms. I don't think here we have important stuff. And they had the tests of this generalization. And this is the conclusion, what I think is important. Like 29 terms were discarded and replaced during the first 28 games. Alpha's performance was initially erratic, but learning showed improvement over time. And the program's play quality was poor at first, but by the end, Alpha was considered a better than average player. So compared against like the previous route learning, this is interesting to notice, and we will do the comparison between them in a moment. I think we can also skip this, and also we skip this. Cool. So let's summarize and conclude what they observed: route learning versus generalization. So just brief recall, like route learning, we have this fixed polynomial, then we evaluate it recursively, then we choose the best play to arrive at our best chance of success. And generalization, we play based on a polynomial that can that we can like more accurately estimate our future score based on our current score. So we try to be as precise as possible on our current position instead of simulating them all. Cool. So the strengths of route learning was that we learned strong opening moves. We had excellent endgame play, particularly when we had a piece advantage, but we struggled during the middle game, often lacking the strategic depth to handle complex positions. And generalization, the strengths were the opposite. So we had like a strong middle game because we could handle complex situations with many possible outcomes, and we can adapt well to varied conditions and quickly use general patterns to dominate when it has a piece advantage. But we had like weak opening moves, and we struggled in specialized endgames. So yeah, because like the generalization tries to, it doesn't have like that sense of winning that route learning has with some simulation. So it's hard to find the best opening position or to conclude the game. So it's pretty interesting comparison. When to use each learning approach, because they are proposing those as algorithms, like the consequences of actions are delayed, route learning is preferred, or highly specialized techniques like opening and game. So in generalization works best in complex large state space. So we cannot simulate every possible combination in a middle game, and it's kind of hard to see like what is good or what is bad because search space is too big. Like we cannot simulate with route learning, so we use generalization and try to avoid excessive computation by estimating our future score. They also propose to do the combining of each of both approaches. This is future work from the paper. And they also like remark that we can use generalization first, then route learning. We can switch once we have a good polynomial, then we can avoid like using it and start to do the route thing to see the delayed rewards. And as a conclusions, this is like a specific print screen of the paper. And they say, as a result of these experiments, one can say with some certainty that it's now possible to devise learning schemes that will greatly outperform an average person, and that such learning schemes may eventually be economically feasible and applied to real-life problems. So, yeah, 65 years later, I think it's interesting to see what people have concluded at the time. And yeah, I think it's the end. So yeah, a lot of stuff. I hope that I could give some analogies and details about like how people came up with some ideas. And if you guys want to comment something or want some questions, feel free to ask.
Really interesting, Gabriel. Really interesting. I think like when you're presenting the paper, it reminded me, of course, a different game, right? But IBM, like almost 4 years later, right, in the 90s, had like Deep Blue that defeated Kasparov, and that was the big thing, right? And I think it's funny, like you think like 4 years from this paper almost, right, and then you get into Deep Blue and then chess. And when you think about the evolution, right, of technology, how fast things are, right? So you go from Go to like video games, right, and like team video games, right? So you have like how they cooperate between themselves, and and of course, like during these 4 years, we have like the evolution of like the computer, the winter of AI, and everything else. But I think it's really interesting. I think about like going back 4 years would be like 1985, right? I say
Yes.
like, oh, how like how things changed, right? I think it's like the divide. We cannot even fathom like similarities between computers in 1985, right? Let
Yes.
alone uh, like 10 years, like 5 years ago, we had ChatGPT, right? Of course, now this is more specialized AI, but I think it really showed like the progress.
Yeah, but I think it's interesting that some problems are still the same.
Yeah,
Like coming up with what's important to the scoring polynomial. Like we still have those problems here.
yeah, and,
uh, how
and
to
like
choose like the terms and etc. Like they have this pretty simple and raw approach, and we come up with very complex algorithms to do that, but we haven't like solved this definitely for any generic problem available. We have this two specialization, and like this is kind of the first paper, and uh, they like mentioned challenges that actually were challenges.
and also just to finish here, I think is also you mentioned in the paper, right? Like how one of the limitations is still computational power, and how, not only power, but how we are able to fit the data,
Yes.
right? Of course, now it's to a much larger degree, right?
Yeah, but we also blame the data, right?
Yeah, yeah,
Now we cannot store all data, so that's why we are not playing well. Like the first paper also said that.
yeah.
It's cool.
Henrique?
Yeah, very good choice of paper. Very interesting to see the history of something I'm very interested in. It's actually the thing that got me into AI when I watched the Deep Minds documentary, that when they defeated Lisa Doll in AlphaGo. That was pretty interesting, and that's what got me into AI. So it's really interesting to see the history, and even before Kasparov's business.
Yes.
But yeah, I'm also very interested in that kind of thing. However, one thing that I was never able to solve, and this is the question here: how do you think? What is the best way that solving these kinds of problems, like solving checkers, solving Go, solving chess, or whatever, or even how you said Alpha, OpenAI, they used the reinforcement learning to beat the world champions in StarCraft 2 and Dota 2. And we know that OpenAI was able to provide to create one of the most interesting products ever, right? ChatGPT, GPT in general. But that's the thing. How do you bridge that gap between solving an extremely interesting but very well-defined problem like solving a video game? Not even a video game, but even those very specific games, combinatorial, and actually creating a very interesting product that is useful in the real world, right? So how do you think we should do to do something in that direction, right?
Yeah, I have no idea. I don't know. Interesting problems and interesting solutions. I think they change, and the paper kind of says this at the beginning. Like we have two methods of learning. We have this randomly switching nets, which are general to any problem, etc. And we have this specific net that is specialized and requires reprogramming based on the problem. And I think we are still, even with all those products, we are still on the second approach of learning. We are still specializing nets for our specific problems. We don't have general switching nets. Even with all that analogies and with the brain and like general tasks and etc. So I think important products and solutions will depend on more on the problems that you want to solve than on the solutions itself, because we are still like working problem to problem and task to task, even with those very high highly complex and huge models that we currently have. So yeah, I don't know. I think it's more of a human question than a technology question, if I got it correctly.
Well, I do have some ideas, but yeah, I don't. My point is, how do we get from being OpenAI developing those very fun things to an actual product, right? And yeah, I have an idea, and I think the main thing is to not. I don't think OpenAI used the models they developed for defeating the world champions in Dota 2 or StarCraft, but I think what they learned in doing those things, the research they had to do to actually be able to do those things, was actually used in doing something else. In another
for
product.
sure, for sure.
It's about the techniques and methodologies and what you learn in the process, right? I think that's
yes, I think so. Yeah, yeah. Because then you can implement like more complex stuff and solve more complex problems.